Now let's do this example, right? So for DC equivalent circuit of this amplifier to be analyzed is this one, right? Open all the capacitors. So this will be removed, this terminal will be removed. So you would be having only this part. It means your DC is flowing only in this portion of the circuit, right? We have already did, right? So we can also Thévenize this terminal at the base to make it more simple, right? Now you have two loops, right? This one and this one. Basically, after Thevenizing, you actually have a Thevenized voltage VBB of this, having this relation, and this RB, the parallel combination of R1 and R2 of having this relation, right? So we already have all the values. So when we put, we get this Thevenin voltage and this RB resistance, R Thevenin, right? So now we are having two loops, right, to be solved for DC load line and DC Q point. So for load line first, Kirchhoff's equation at this output loop, VCC, VRC, VCE, no RE, so no VRE, right? Or using Ohm's law, we can replace this V is equal to IR. So VRC is ICRC, right? And for extreme points of the load line, so extreme points would be at the X and Y intercept, right? Because your load line exists in the first quadrant and having an X coordinate and a Y coordinate, right? So putting VCE is equal to 0 because this is your X axis for the output characteristics curve and this is your Y axis, right? So for extreme y intercept is this one, so you have to put your X axis is equal to 0. You will get the IC saturation maximum value is equal to VCC by RC, right? And once we put all the given values, we have IC saturation maximum value of this one, right? For x-intercept, we have to put the y coordinate 0 of this equation, right? So VCE cutoff is equal to VCC, right? Now we can draw it because we have VCC is equal to 16 volt, right? So we have to draw the axis VCE total, IC total. Although we have only DC values, so it's okay for the time being, no AC, so total is equal to DC only. So y-intercept is 11.43 milliampere because this whole axis is in milliampere, and VCE currently have only DC value of cutoff point at 16, right? So this is your load line, 2 points, you can join it and you can get the load line, right? And recall that the slope of this line is actually the combination of the resistance at the output loop, right? And what is the resistance? Minus 1 upon R out DC. What is R out DC here? Is RC, right? Please check with the previous examples, right? Currently, I will just tell you, just rewrite this equation in the form of y is equal to mx plus c. Then you will get IC is equal to minus 1 by RC VCE. So minus 1 by RC is your slope, plus the y-intercept VCC divided by RC. This is the y-intercept VCC by RC, right? This is the x-intercept if you put in this equation. And the slope is minus 1 by RC. Minus 1 by, what is R here? RC. You have only external component, RC here only, right? We are not talking about the output resistance between collector and emitter within this. This currently is actually incorporated in this VCE. You have a VCE, it means you have something in it. You are not going to model it for DC, right? We model it in for AC amplification part, right? So far you are asked to draw the DC load line. You have drawn the DC load line. You are not asked to draw the DC load line on the output side as well as at the input side. Then you can only draw the load line for the output loop side and your work will be finished. But if you are asked to draw the load lines, it means you have to draw the load line at the output side and at the input side as well. So let's do the same thing for the input side load line. So for input loop, you can write the same equation, right? Similar equation by using Kirchhoff's voltage law. VBB is equal to VRB plus VBE. IC is beta IB, so we can write VRB is equal to IBRB, and IB is IC by beta, right? So for extreme points of X and Y coordinate of the load line for the input characteristics curve. Input characteristics curve is actually drawn in between VBE and IC, right? So we have to put VB is equal to 0 for saturation, maximum saturation point at the y-axis, right? And when we put this, we got this value. So at the input characteristics curve, your y-axis will be at 29.64 milliampere, right? Saturation. Please don't be panic. These are not same. It doesn't matter because this load line is saying that you can achieve this point if you cut your y-axis. Actually, you cannot cut with 0 VCE. Your characteristics curve will not pass this value. This is just this line is saying, because you can operate in your transistor only when this line and the characteristics curve have an intersect. So this is just an hypothetical line, but obviously all other points on this line which actually also satisfy the characteristics curves of the transistor is your desired point. That's why you use this point and also this point to draw the line, right? Same is here. Okay, so when we put IC is equal to 0 to find the x-intercept, you get VBE is equal to VBB, right? This is again the hypothetical point, because for this much VBE you can have good currents, but your characteristics curve does not allow you, right? Your characteristics curve at the input side is this kind of nature, right? So we are not going to draw that. So for DC load line at the input side, you must be having IC with respect to VBE total currently having only DC values, so only DC value will be equal to the total values, and your extreme points should be marked here and then joined to get the DC load line. Obviously your transistor only works when this load line finds an intercept with the characteristics curve of the transistor. Otherwise all other points will not be achievable, right? So it's okay, we have designed this. So again, this R input DC will be the resistance, the total resistance of the input loop. Currently you have only RB, not RE. So it means you are only having 1 minus 1 by RB. So you can find it here, right? Oops, we forgot to write a bracket here, right? Although we have used the correct relation here, there should be a bracket here. Let's correct it, right? Fine now. So I see if we transform this equation to y is equal to mx plus c, we would be having IC is equal to minus beta by RB VBE plus beta by RB VBB, right? Beta by VBB RB is your y-intercept, and your slope would be minus beta by RB, right? Why beta by RB? Because we are having IC here. If we use IB, because of VBE, only minus 1 by RDC, right? So actually in this RNDC, we have beta inside. So it's RB by beta. Okay. So far we have drawn the DC load lines for input side and for the output. If you are asked to draw the DC load line or only for output loop, this much work is enough, right? So let's go ahead to find the Q point, and we have to locate it on the DC load line. We have to draw on the load line we have already drawn. So we have drawn already the load lines, and we have actually wrote the Kirchhoff's voltage equation on the input loop and on the output loop sides, right? So we will be requiring this, but no more hypothetical computation for x and y intercept to draw the load line, right? So now we have to find the solution of these two equations. Where the VBE is, where is the IC, where is the VCE for our available values of VCC and RC and so on, right? So if you have been given the basic parameters, the IS of this transistor, right? Besides the beta you are already given as 300 and VT and VA. But if you would be having given IS, the scale current, and one of the test point, that what would be the IC for what value of VBE, then you can use that information and the basic transistor equation IS is equal to power VBE upon VT to iterate with this equation to get the VBE and IC, exact value of VBE and IB. We did it already, right? But we also said at that time that if you are not given that things and if you are asked that this circuit is nothing but an amplifier that you have to analyze, then your VBE would be nearby zero point 0.7, so you can take it 0.7, right? So we took VBEQ is equal to 0.7, right? And when we put this VBE, we already have beta, RB, VBB, we got ICQ. And when we put this ICQ here, we have RC, we have VCC, we can get VCEQ is equal to this one. And now this is your Q point at the output side, this is your Q point at the input side, right? So just place it on the load lines, right? So this is VCEQ and this is ICQ, right? And when you mark, these curves must be on the load line that you have drawn. It means you are doing fine. Same would be the case here. Here and then this current, and when you extrapolate this point, it must be at the load line. So this is what you have found the Q point and located it on the both the Q points on the output and input load line accordingly. So now the AC equivalent circuit and its parameters. This was the C part, right? So we already know the AC equivalent circuit of this one can be found by shortening this voltage source. So short with the ground, then these terminals will also be become grounded, and also the capacitor will behave as short circuited because it would be its value would be taken according to the frequency of operation, so it will be considered as short circuit. So your AC equivalent circuit would be this one, and then we can also Theveninize it for these resistances, so we can have RB, right? This one. So we have already done this already, right? But what we have done in this lecture is now this circuit can further be simplified by writing for small AC signals by writing a model, a schematic of model of this transistor in terms of this transistor, then your circuit become more easier. So currently I am using hybrid pi model. Why? Now I am going to give you the logic behind taking hybrid pi model instead of T model is that in your AC equivalent circuit, not this circuit, basic, not the amplifier circuit, in your AC equivalent circuit, if the emitter terminal is grounded, right, then it's better to use hybrid pi model. Why? We will do this later when we will do one example for both pi and T model. At this time, please just allow me to go through at least the computations of finding the AC parameters of by taking only one model suitable for this configuration. So hybrid pi model is found suitable, right? So now you have replaced your transistor with this one. Now other circuit will remain the same. So your emitter is grounded, put ground here. Your base is having this circuit, put it here. Your collector has RC to ground, put it here, and you have output here. You have output here with respect to ground, right? So you with respect to ground, this ground is same, right? You have this one, and you have an output resistance. right?